Okay, so in this chapter and the next chapter, we're going to start talking about heat and thermodynamics, which is heat in motion. We've been giving clues throughout this class about the nature of heat and temperature in different materials. In the last chapter, when we talked about fluids, we kind of said that temperature, say of a gas or of a liquid, was related to the internal kinetic energy of the gas molecules. And in these next two chapters, we're going to dive in a lot deeper and ask, what really is heat? How does it flow from one object to another? And when does it flow from one object to another? Right? And there's actually a fun kind of historical irony in discussing chapters on heat immediately after chapters on fluids. In the, say, late 18th century and earlier, scientists actually believed that heat was a fluid. People thought that heat was a substance, like a self-repelling gas. There was some debate about whether cold was a separate gas or if cold was just the absence of this kind of caloric fluid, as it was called. Nowadays we have a much better understanding of what heat actually is, and so fun historical ironies aside, that's what we'll be talking about. So we'll start out in section 8.1 of the lecture notes, which talks about stoves, and more generally, just imagining I have like a burning log or some other hot object, and I grew up somewhere that was really quite cold, and so doesn't matter now that I live in Atlanta, but this used to be more important to me. When you're, say, sitting in front of a fire, what's actually going on? What is it that's producing the light that we see and also the heat that we feel? And why is it that we feel the heat of a fire, even if we're not actually physically in contact with it? And even if the air in between us and the fire might still be cooler, why do we have these sensations of heat? So that's what we'll dive into in this first chunk of the lecture notes. And first, I want to talk about thermal energy in solids. Thermal energy in solids. Okay, so again, we said that the thermal energy of a gas was associated with internal kinetic energy of these gas particles flying around at very high speeds. And what we meant by internal kinetic energy was that the component parts of the gas, all of these individual molecules, on their own, each one of them had a lot of kinetic energy, but the center of mass of the whole gas was not moving, right? So if I just have the air in this room, on average, the air in this room is staying in the same position, even though each individual gas particle is moving very quickly, right? So there's no kind of net kinetic energy of this gas flowing, but there is an internal kinetic energy associated with each individual particle, right? And if there was a wind, say, like a breeze from the fan that's right next to me, then the gas could have both internal kinetic energy and what we've just been calling normal kinetic energy, as the center of mass of, say, at least some portion of gas is moving in a coherent direction. Okay. So we've met kind of thermal energy in gases, and we know that thermal energy has been generated by other things we've considered in this class. Like we talked about the work that you do to slide, say, a heavy bookcase across the floor. The reason that the bookcase doesn't keep accelerating as you apply forces to it is that friction is trying to slow it down, and the work that you're doing is getting dissipated into this kind of frictional heating. Okay. So thermal energy, more generally, thermal energy is what I'll say the portion of an object, the portion of the internal energy of a thing, an object or a material, associated with temperature. And this might seem at first like a very circular definition. We will dive deeper and deeper into what we really mean by this sentence. But let me first start contrasting this with other things that I could have said here, right? So first, I said there's a portion of the internal energy of an object associated with temperature. So thermal energy does not depend on external forces, for instance. So if I have, this like pen stand for this writing tablet, as I lift it up into the air, I'm changing something about its potential energy, the gravitational potential energy this object has, but I'm doing absolutely nothing to the temperature of this object, right? So I've got this thing, I lift it up to give it gravitational potential energy, or I move it around to give it kind of external kinetic energy, and none of those things none of those things are the thermal energy of this object. Okay. So first, thermal energy is associated with internal energies of an object, not with external energies of how it's moving or interacting with other things in the world. Okay. And I say it's a portion of the internal energy because actually most internal energy that an object has is not associated with the thermal energy that the object has. So for instance, the molecules making up the plastic that this pen is composed of, those are formed by atoms being in chemically bound states with one another. So they have these chemical bonds that connect them to nearby atoms. And those chemical bonds also have a lot of chemical potential energy, right? But chemical potential energy is not the thermal energy of an object. So that's a type of internal energy stored by an object that is not something we measure with temperature. Similarly, the atoms themselves, the protons in the nucleus of an atom, are held together by what we'll just call like nuclear potential energies in this case. That's the kind of thing that gets released in a nuclear reactor or when you detonate a nuclear bomb. Again, there's a massive amount of potential energy stored in the atoms themselves, but it's not associated with the temperature of the object. It's a different type of internal energy. It's not thermal energy. Okay, so if those are lots of things that thermal energy isn't, in solids, what is thermal energy? In solids, thermal energy is basically made up of the internal kinetic energy of the atoms composing an object, from the atoms like wiggling and oscillating back and forth, both within a single molecule and also in the way that molecules like to sit together. So for instance, one of the things that I said in a previous chapter was that microscopically, if you look at how atoms in a solid are arranged, here I'm drawing like a particular crystalline solid, you can see that the atoms want to be in very specific places relative to one another, right? But in a solid, these atoms are not just sitting perfectly still. Instead, each atom is kind of wiggling and vibrating and oscillating back and forth. They have a particular distance that they want to sit away from other atoms. If they get closer to other atoms, they get repelled. If they get too far away from other atoms, they get pulled back in, almost as if there's like effective springs holding atoms in place where they want to be. And that's true both of just individual atoms sitting in a lattice or atoms in a molecule that is itself composing a bigger material, right? So just like in gases, actually, in solids, the things that make up these solids have a type of internal kinetic energy that come from them kind of jiggling and oscillating and dancing around the kind of positions that they usually sit in. Okay. One thing that's kind of interesting to note is, if you look at, say, two atoms, the chemical, if they're in a molecule, the chemical bond between them, or if they're in like a lattice just of other atoms, the kind of interactions between them, like I said, it's almost as if there's a spring connecting them, making them have a particular equilibrium separation from one another. There's a distance that they want to sit apart from each other, where the attractive forces and the repulsive forces that they experience balance out. An interesting thing about these kind of atomic scale springs, which come from chemical bonds, or electron interactions, the electrons in one atom interacting with the electrons of another atom, all kinds of different things. An interesting thing about these springs is that they aren't symmetrical. So if I have a macroscopic spring, the kind of thing where we were imagining, two balls connected with the kind of spring that we have inside of our pens or anything like that, Hooke's law tells us that the forces that you experience is just the negative of the displacement, and it's symmetrical. So if you displace in a little bit, you feel an outward force, and if you displace out a little bit, you feel an inward force, which is the same. Well, at the atomic scale, there can start to be asymmetries between the two directions that forces get exerted by. And so if atoms are too close together, they feel a really strong repulsive force. And if they get a little bit too far apart, they feel an attraction, but it's weaker than the equivalent repulsion they feel if they're that much closer than they want to be. Because are not as, let's just say, symmetrical as the springs in Hooke's law. Another way of saying this is that, we said Hooke's law has some elastic limit, a range of deformations over which this linear, force is negative distortion applies. And these atomic scale springs can be in the non-linear or non-elastic regime of behavior. So because these atomic scale springs are not symmetrical, as an object's temperature rises, well, what does it mean for the temperature to rise? The internal kinetic energy of that object is going to go up, and so these like atoms are kind of wiggling and dancing with bigger and bigger amplitude oscillations. But because the springs are not symmetrical, as the temperature rises, on average, atoms in a solid get a little bit farther apart. Get a little bit farther apart. Okay, and this is sometimes described by the coefficient of thermal expansion. Which is sometimes labeled by this Greek letter alpha. The coefficient of thermal expansion measures a fractional change in an object's volume per change in temperature. Okay, and so in equations, and you don't need to remember this equation particularly, in equations it might look like something like the coefficient associated with thermal expansion of an object is equal to 1 over the volume of the object times the change in volume per change in temperature. And let me just give you an example of this. So for instance, iron. I looked this up just before we started. Iron has a coefficient of thermal expansion, which is like 3.6 times 10 to the minus 5 per degree Kelvin. Okay. What this means is that for every degree Kelvin you heat up a chunk of iron, and 1 degree Kelvin is the same as 1 degree Celsius change, which is the same as 1.8 degree Fahrenheit change. So for every degree Celsius you change the temperature of a chunk of iron, the iron will grow by this fraction. So for instance, for every degree K increase, a chunk of iron gets 1 point this much bigger, a tiny bit bigger. Okay. If I just multiply this number by 50 degrees, by 50, just so that I don't have to write as many zeros, 5 times this is 0.18. And so equivalently, if I heat a chunk of iron by 50 Kelvin, its volume will increase by about 0.2%. By 0.18%. Okay. You know, these are fractional changes in the size of an object, and it kind of grows in every direction. So if I have a cube of iron, the cube kind of uniformly gets a little bit bigger as I increase the temperature. Right? And, you know, the fact that materials change their size a little bit with temperature, so they shrink when they get colder, they grow when they get warmer, is something that maybe you've experienced in the world around you. For instance, if you have like a glass jar of, you know, whatever, salsa with a metal lid, and it's really hard to get unstuck, if you run the metal lid under hot water, it can be easier to open because the coefficient of volume expansion for metal is bigger than for glass. And so the metal lid will grow by a tiny bit more than the glass grows by, and so it will be a little bit looser and a little bit easier to unscrew. Okay, so that's kind of a fun property that is ultimately coming from the way thermal energy is present in a solid in the first place. Because thermal energy is associated with this like internal kinetic energy of atoms moving around, and because the effective springs holding atoms in the right place aren't symmetrical, as a result of that, solids have this property that they'll get bigger as they get hotter by a little bit. by a little bit. Okay, so similar to the kinetic energy that goes into temperature in a fluid, in these solids we have this kind of disordered dance of particles vibrating around, contributing to the thermal energy of a solid. We'll talk a lot more about how heat flows from one object to another in the next section, but intuitively you can kind of think, well, if I have one object that's really hot, its atoms are kind of vibrating and dancing around more than if I put it right next to a colder atom, or a colder object. And so at the surface between these two things, the atoms that are kind of moving around a lot in the hot object keep bumping into the atoms in the colder object. And those collisions are kind of going to disproportionately trade some of the kinetic energy the atoms in this object has into the atoms that this object has, slowly kind of giving it some of this internal kinetic energy. Great. We'll think about the three kind of primary mechanisms by which that process actually happens, by which heat actually flows from one object to another in the next section. But first, I want to talk about two things. One, what's actually going on when something is on fire, just because that's kind of a, fun thing to talk about. But I also want to talk about other ways of characterizing how much an object warms up as you add heat to it. So let's, in the notes, these are in this order, so I'll do it in this order, although I think I should have flip-flopped them. So again, just kind of thinking at the molecular level, what's happening when you have a piece of wood that's on fire? The answer is basically that when you have a piece of wood that's not on fire, a lot of wood is composed of these molecules called cellulose. And cellulose is basically a long chain of carbon atoms. These are all like carbon atoms, carbons, connected to little hydrogen atoms. Okay, so wood is this, or at least some of the molecules in wood are these long bound chains of carbons and hydrogens stuck together with chemical bonds. And it turns out, both carbon and hydrogen can form much tighter chemical bonds, not with each other, but with the oxygen in the air around us, right? But because they're currently bound together in these, wood molecules, wood won't just spontaneously come apart and join up with oxygen atoms. Okay, but if you have a match, you can give, a lot of heat to. So I have a match, providing enough kind of energy to break apart these chemical bonds holding the carbons and hydrogens together. And once you've done that, the carbons and the hydrogens are free to form new chemical bonds with oxygens in the gas around. Okay. So you have this process by which carbons and hydrogens, I believe in wood it's mostly a bunch of CH2s, a bunch of these come apart from each other and form carbon dioxide and bits of water, H2Os, so CO2s and H2Os. And, the amount of chemical potential energy stored in this object is a lot bigger than the total amount of chemical potential energy stored in these objects. The fact that they form tighter chemical bonds over here, let's think about that. Like, why does that mean they have less chemical potential energy? It's just like if you're in, Earth's gravitational field. When you lift something up, you're giving it more gravitational potential energy. When you bring it closer to the Earth's surface, so it forms a tighter, bond with the Earth, if you will, it has less gravitational potential energy. Okay, so less total chemical potential energy. Okay, so what does this process look like? If I kind of imagine on this axis I have chemical potential energy, and maybe this is like time, before these molecules have come apart, they have a certain amount of chemical potential energy, and then when I add heat, that gives them enough energy to break apart and then form new chemical bonds with the oxygen atoms. That drops the total amount of chemical potential energy. What happens to all of this energy here? Well, it goes into light and heat, and the heat from this chemical reaction is then enough to break apart other cellulose molecules in the wood. And so you get this self-sustaining chemical reaction whereby the heat generated by the breakup of one molecule is enough to break apart another molecule. Okay, and that's how, I don't know, that's how fireworks or burning objects work, I suppose. So that was just a quick aside. Before we get into the three ways that heat can actually flow, let me talk about section 8.1.2, warming an object up, which is just, I want to make sure that we can characterize, because we're going to talk about how heat flows. And heat, thermal energy, it's an energy, so we might say an object has a certain amount of joules of thermal energy, or a certain number of joules of thermal energy are flowing from one object to another per amount of time. And you might wonder, well, as that much energy is flowing, how much is that actually changing the temperature of another object? Right? And the heat capacity of an object refers to how much thermal energy is needed in order to raise its temperature by 1 degree. So is how much thermal energy you need to raise temperature by 1 degree. By one unit of whatever scale you're measuring temperature with. By 1 degree. And by 1 degree. And the heat capacity of something depends both on what that object is made out of. So, heating up a chunk of iron takes a very different amount of energy than heating up a chunk of water. Something that if you've ever tried to boil water in a cast iron pan or something like that. But it also depends on how big the object is, how much stuff the object has. And that's because the more atoms an object has, when you're adding thermal energy, you need to give enough thermal energy to make all of those atoms wiggle and dance by some new bigger amount. Okay. So heat capacity is kind of like this property of the object as a whole. It's sometimes easier to talk about specific heat. So instead, we'll characterize materials by specific heat. Okay, and specific heat is whatever the heat capacity of a substance is, and that's something that depends on the substance and the mass, divided by the mass, right? So we have something that depends both on composition and amount of stuff. We divide it by the amount of stuff to get a quantity which just depends on what type of object we're talking about. Okay, so specific heat has SI units of joules per kilogram per Kelvin. Okay, so it says how many joules of energy do I need to put into this object per amount of mass of that object per degree that I want to change the temperature. So joules per kilogram per Kelvin. Okay. Now, metals tend to have actually relatively small specific heats, and that means they're easier to heat up, right? So some common values, say something like, copper. Copper has a specific heat of something like 386 joules per kilogram Kelvin. Water, it takes a lot more energy to heat up a kilogram of water by 1 degree than it does to heat up a kilogram of copper by 1 degree. Water is closer to 4190 joules per kilogram Kelvin. Kilogram times Kelvin. And air at atmospheric pressure has a specific heat which is kind of in between these two things, something like 1001 joules per kilogram Kelvin. Earlier we thought a little bit about how much energy Emery uses in the context of how many wind turbines would it take to run Emery's energy budget. And, let's continue to think about what the meaning of some of these values of specific heat are in the context of heating and cooling down rooms, right? So, for example, the volume of, say, a dorm room might be, just ballpark, 30 meters cubed. And the amount of air in that volume might be something like, I worked this out earlier, say 37.6 kilograms. Remember, the density of air is a little bit bigger than 1 kilogram per cubic meter. Okay, and so the specific heat of air, 1,001 joules per kilogram per Kelvin, tells us that if we want to heat up all of the air in your dorm room by 1 degree Celsius, so heating room by 1 degree Celsius, which is the same as heating it up by 1 degree Kelvin, requires about 38,000 joules of energy in total. I have a certain mass of air, I have a certain, I want to change its temperature by 1 degree, and this specific heat tells me how many joules per kilogram per degree I need to add in order to change that temperature, okay? So if it's a cold day in Atlanta, a very cold day by Atlanta standards, so for instance, like in the winter, if it's -5 degrees Celsius outside and 20 degrees Celsius inside, and you, for whatever reason, open up your window and let your room then, pretty quickly fills up with that blast of cold air, the energetic cost of raising the temperature in the room back from -5 Celsius to 20 Celsius is 25 times that number, right? So that costs, almost 1 million joules of energy, right? And this is essentially one of the reasons why heating and cooling can be an enormous part of the energy budget of something, right? For context, if we say a computer, maybe you have a very high-powered computer and its power supply unit needs like 1 kilowatt, so that's 1,000 watts, 1,000 joules every second. The cost of heating up the room from just opening your window and then closing it again is like running your computer for 1,000 seconds, right? For 1,000 seconds, which is like 15 or 16 minutes, give or take. And as we'll discuss in the next section, heat isn't only changing from just people occasionally opening windows. Buildings are constantly losing heat, and these kind of energetic effects add up really quickly.